Hello and welcome to my video on series, and today we're going to be focusing particularly on the geometric series. We're going to start this video off by discussing what exactly is an infinite series. Okay, so our definition of an infinite series is going to be an expression that takes the form like the one shown on the screen, a1 plus a2 plus a3 and so on. Or you can also write it as sigma notation, where the k is the starting term. The top term, the infinity in this case, is going to be where you go until, and then the general term right here of a of k. And if we could actually just go back to the last slide here, just for general knowledge, these a1, a2, and a3 are all considered terms in this series, particular values for whatever their subscript is. And this one at the end is considered the nth term, which is just the general term of the series. Okay, next we're going to talk about partial sums. And the partial sums of a series form a sequence. So here, S1, that is the partial sum of the first term only, which that's why we have A1. S2, the partial sum up to the second term, A1 plus A2, and so on with S3 as well. We can also represent these sequences with a general term sequence of S to the n is equal to the sum from k equals 1 to n of our general term a of k. Now what this is saying is that up to any n value that you put in, and you go up to that as well, over here, you just keep adding and adding. So this sequence works for any real number that n can go to. Each of these partial sums are represented as finite sums, even though the series itself has no finite value. Now, we say that if the sequence of partial sums has a limit as s approaches has a limit s as n approaches infinity, we say that the series will converge. Otherwise, we say the series will diverge. Now let's address what we all came here for, and that's geometric series. So, I'm sure everyone's probably seen a geometric series before in pre-calculus. This here is a geometric series, as we can see, because to get from one term to the next term, you have to do an operation of multiplication to get there. Now we can also represent the geometric series as an infinite series. So here we'll go, each successive term, and then, followed by the general term right here, and here we have the sigma notation. Now, staying on geometric series, we have some foolproof ways here to find out whether a geometric series will converge or diverge. Now, if you have a geometric series in the form of, like we saw before, the sigma of AR to the n minus 1, infinity from 1, we know that the series will converge if you put it in this form right here, and the absolute value of r is less than 1. This will mean that you have preceding terms that have been multiplied, having or whatever fractioning the previous original term a. Similarly, we can say that if the absolute value of r is greater than or equal to 1, the series will diverge. So why don't we look at an example right now. So here we have a summation from 1 to infinity of 3 times 1/2 to the n minus 1. So let's find out whether or not this series will converge or diverge. So as we saw before, we can tell if a geometric series will diverge or converge based on this. Now, for this past equation that we just shown here again for your convenience, a here will be equal to 3 minus our r of 1/2, and we get that the series will converge to a value of 6. Now let's get another example, but slightly different look here. So we're going to have the series 1 minus 1/2 plus 1/4, yada yada yada. And then we're going to have the general term plus negative 1/2 to the n minus 1 right here. Oop. Oop. Keep having problems. N minus 1. There we go. So the first term is 1. So we're going to put 1 where our a would be. And then 1 minus, and now our r term is going to be negative 1/2. So now when we solve this, we find out that the series will converge to 2/3. Well, that looks bad. Let me fix that real quick. Alright, 2/3. And as you can probably notice at this point, pretty much, as you can see that we've been doing, all absolute values of r that are less than 1 will converge. Now let's try another example but with greater. So let's say our first term was 4, 1 minus, and our r term was 5, okay? In fact, disregard that last bit. I was mistaken there for a second, but if your r is greater than, or 1, don't even bother with that whole a over 1 minus r thing. That's just scrapped as soon as you see this right here. Quick tip. Alright, that's all we have for today. Thanks for watching, everyone. Hope you have better success with all this calculus.